Assalamu alaikum and welcome to lecture number 19. In this lecture we are going to discuss about the linear systems with generalized linear phase. The last topic of this chapter is a linear system with generalized linear phase. So I hope you understand that for the case of frequency selective filters, whether they are band pass or low pass filter or high pass filter, we want that the magnitude response should be constant at the pass band or the band of interest, whereas we want zero phase at the uh, band of interest. Band of interest, you understand, for the case of low pass filter, for from 0 up to some finite value of the filter should have constant magnitude response, and it should also have zero phase shift. But for causal systems, zero phase is not achievable. Hence, there will be some phase distortion that should be allowed. The effect of linear phase with integer slope is a simple time shift, whereas a non-linear phase can have a major effect on the shape of the signal, although the magnitude response is constant, but still it will have effect on the shape of the signal. So it is particularly desirable to design systems that have exactly or approximately linear phase. Filter needs linear phase in order to properly shift every signal by the same amount, like we have discussed in the examples. In the frequency response of LTI systems, there we had a input signal that had three different components, and you saw that the one with the lowest frequency was delayed by more than the one that has the higher frequency. But having exactly linear phase is this constant is slightly stricter than what we actually need for most filters. So we consider formalization. In this lecture we are going to consider the formalization and generalization of notions of linear phase and ideal time delay by considering the class of systems that have constant group delay. System with linear phase. So let's consider an example of the ideal delay system with delay of alpha. So the frequency response over one period is HID equals to E of j omega, and this is equal to e power minus j omega alpha for the frequencies which are less than pi. So this type of system has constant magnitude response, because if you take the magnitude of this one, that will be constant, whereas the principal phase, phase response of this system, if you look at the equation, so this is the phase, so it will be minus omega times alpha. So this is the phase, and it is also, you can see that it is a linear. Similarly, group delay for this system is constant. You understand that taking derivative of the phase response results into what is called as group delay, and because we integrate it, we differentiate it using minus d over d of omega minus alpha minus omega alpha, so it will result into alpha, a positive constant. Now to find the impulse response of this ideal delay system, we take inverse Fourier transform of this frequency response, and we find that the ideal delay system has impulse response which is equal to sinc function, right, where alpha is amount of the delay. So the output of this system using any arbitrary or generalized input which is x of n. So you understand in time domain the output is equal to convolution of the input signal with the impulse response. So taking convolution of this will result into this. I hope you understand the convolution and those things. Now if alpha is integer, then the system is simply a delay shift system, that is input, that is the response of this will be equal to impulse of n minus nd, where nd shows the shift. So because you understand that the impulse is basically identity of the convolution, so whatever you convolve with impulse, it will result into that signal. In case the signal is the impulse is shifted, then the signal will be shifted. So that means whatever you give it at input, the output will be equal to the shifted version of the input, which is by amount of nd. Now as we have seen that if the group delay alpha is positive, so simply if we talk here, if nd is positive, in that case you understand the signal will be shifted right, or you can also say that the signal will be delayed by amount of nd. Similarly, if nd is negative, in that case the signal will be shifted left, right? For negative of nd it will be shifted left, and for positive of nd it will be shifted right. So shift left is basically advanced, what we call it, and a shift right will be the delayed version. So that means the group delay alpha is positive, the time shift is time delay, right? That's pretty straightforward, right? You understand from basic theory of the signals and system. And similarly, if alpha is negative, in that case it will be the advanced version, right? So the output signal will be advanced by amount of nd. So let's consider a more general frequency response with a linear phase. So that is represented as h magnitude response times the phase response. Here the magnitude response may not be constant. So this is represented by the block diagram here, that we have a cascade of the magnitude response and the linear phase response. So xn is filtered by zero phase frequency response, and the filter output is then time shifted by amount of alpha units. If h of j h e j omega, which is the frequency response, is a linear phase ideal low pass filter, in that case we can say I hope this you are familiar with this expression, because for a ideal low pass filter we have 1, right? The this is equal to 1 for omega is less than the cutoff frequency, okay, and 0 otherwise. So we have some shift introduced here. So the ideal low pass filter will have response equals to e power minus j omega alpha for absolute of omega is less than omega c, and when absolute, you understand, we take both the negative frequencies and positive frequencies. So for a low pass filter we have the frequency spectrum, which let me draw here. This is minus omega c and this is plus omega c. So if frequency, if the input has frequency in this range, so in this range we have output equals to this one, right? So for this we can find the impulse response, right? So taking the inverse Fourier of this one will result into the impulse response, which corresponds to HLP of n sine omega c n minus alpha over pi n minus alpha. You understand alpha is representing the shift. So in case alpha equals to 0, then we have same function which normally we have for the ideal low pass filter. So let's consider an example with the systems with linear phase. So this is example, okay, in the textbook, that is signal discrete time signal processing by Alan V. Oppenheim. So you understand that most of the material present in this lecture are taken from this book. So this ideal low pass filter has cutoff frequency which is equal to 0.4 pi, and for example the delay is 5 units because alpha is positive, so that means it is delayed version, okay, by 5 units. When alpha is integer, the impulse response is symmetric about n equals to nd, or it's about the alpha. So to show this, we can write that HLP 2 times nd minus n. So you understand this term represents the reflected, right? Because n is replaced by minus n and 2 nd, so that means it's reflected by 2 times nd. Nd represents the amount of shift and reflected. Okay, so that means we replace n with 2 times nd minus n in the previous slides, or let me write here. Let's try here, in fact. So okay, so if you recall the previous slide, so in the previous slide we had HLP of n equals to sine omega c n minus alpha over pi n minus alpha. So now we reflect and shift and reflect, shift by 2 times nd and then reflect, so we get this expression. So on simplification, this is 2 nd minus n minus nd. So you understand this will result into, because this 2 times nd minus nd will result into nd minus n, and this is pi nd minus n. So taking minus common, so we are left with uh, n minus nd over n minus nd, again minus here, so this minus become plus. So you are left with sine omega c n minus nd over pi n minus nd, which is equal to HLP, as we have seen shown on the previous slide. So that means this side equals to this one, so that shows that the impulse response is basically symmetric about nd. Now if we take the second case where we have omega c, we keep the same frequency but the shift is basically 4.5 unit. In that case, if we, right, so shown is here graph for the this part A, where we assume that the amount of shift is by integer factor. In the second case, we see that we keep the same frequency, but now we keep the shift by 4.5 units. So because this is non-integer shift, right? So that means in the previous case n was symmetric about nd. Again if we see, so it is again symmetric by alpha equals to nd 4.5 unit shift, which is a non-integer. So if we see that so in this case again the point of symmetry is alpha, although alpha is not an integer. For this case, we can also show that 2 alpha minus nd equals to HLP, and that is its symmetric about. So it is not possible to shift the sequence to obtain the even sequence that has zero phase. This is typical of the case when the linear phase corresponds to an integer plus 1/2. If you see that it is 4.5, so that means it's integer plus 1/2. The third case we are going to consider is the case when the shift is 4.3 units. So in this case there is no symmetry at all. So I hope by looking at the graph you can, or the figure, you can easily point out these important points. So in general, linear phase system has frequency response equal to this one, that's magnitude response, and this is the phase response. If 2 alpha is an integer, that is, if alpha is an integer or integer plus 1/2, as we have seen in the previous example, the corresponding impulse response has even symmetry about alpha, that is alpha h of 2 alpha minus n equals to h of n. But if 2 alpha is not an integer, in that case IR will not have even symmetry, but it will have still linear phase and constant group delay. I think you can see from the equation, and as we have discussed in the previous example. So generalized linear phase, as we talked on in the previous slides, we don't actually always need linear filters. In the earlier discussion on the linear phase systems, we discussed the class of system whose frequency response is of this form: a real valued non-negative function of omega multiplied by the linear phase term. You understand this is a linear phase. Now to define the generalized definition of the linear phase, we say a system is called a generalized linear phase system if its frequency response can be expressed in the form the frequency response is h of e j omega, and it should be a e power j omega times e power j alpha omega plus j beta, where alpha and beta are constants and a e j omega is a real, and it's possibly bipolar. That means it can have positive as well as the negative values, and it is function of the omega. For such systems, the phase consists of constant terms added to the linear function, that is alpha omega. So we have minus omega alpha plus beta, and if you look at this one, this is the equation for a straight line. If we ignore the discontinuities that result from the addition of constant phase, or all are part of the band, then the system can be characterized by constant group delay. Hence, the class of systems such that the group delay is constant have a linear phase of the more general form argument of h of j omega. You understand that's this one, right? So this is equal to beta minus omega alpha, and both beta and alpha are real constants. Based on the example we have done, we see that impulse response of the linear phase system may have symmetry about alpha if 2 alpha is an integer use. So in the previous example, in one case we have alpha equals to 5, whereas in the second case we had alpha equals to 4.5, and we found that the impulse response was symmetric. For the system with generalized linear phase, we can write it like this, as we also mentioned in the previous slide. So for this system, necessary condition to have constant delay is that h of n summing from minus infinity up to infinity sine omega n minus alpha plus beta should be 0 for all values of omega. So one set of conditions that satisfies this equation is if beta equals to 0 or pi 2 times alpha should be an integer multiple, and alpha h of 2 alpha minus n will be h of n. So a e power j omega is an even function of omega. Another set of conditions that satisfy equation 4 is that if beta equals to 3 pi by 2 or pi by 2, again m is an integer, so we have h of 2 alpha minus n equals to minus h of n. In this case, aej omega is an odd function of omega. These two sets of conditions guarantee generalized linear phase or the constant group delay. But there are other systems that also satisfy equation 3 without these symmetry conditions. Causal generalized linear phase systems. So in case of causal FIR systems have generalized linear phase if they have impulse response length equals to m plus 1 and satisfy either equation 5 or equation 6. So if h of n equals to h of m minus n for this range and 0 otherwise, then h of ej omega equals to ae e power j omega e power minus j omega m by 2, where aej omega is an even function of the omega. If h of n equals to minus h of m minus n for this range and 0 otherwise, then h of ej omega equals to j a naught e power j omega e power minus j omega m by 2, or a naught e j omega e power minus j omega m by 2 plus j pi by 2, where a naught e j omega is an odd function of frequency. In both cases, the length of IR is m plus 1 samples. Equation 7 and equation 8 are sufficient to guarantee a causal system with the generalized linear phase. So here is classification of the causal generalized linear phase systems into 4 types. So these are based on the even odd nature of the M and even odd symmetry of the type of impulse response. So these are type 1, type 2, type 3 and type 4. The expression for the frequency response of FIR. The expression for the linear phase response of FIR linear systems are useful in filter design and understanding some of the properties of such system. In deriving these expression, it is significantly different expression results depending on the type of symmetry and whether M is even or odd. For this reason, it is generally useful to define 4 types of FIR generalized linear phase systems as described here. Type 1 system is defined as a system that has a symmetric impulse response. So in this case, m is an even integer, so the delay will be m by 2, which is also an integer. So the frequency response is given as h of ej omega summation n running from 0 up to m, h of n e power minus j omega n. Or it can be written as h of ej omega equals to e power minus j omega m by 2 into summation k running from 0 up to m by 2 ak cos omega k, where ak's are equals to 2 times h of m by 2 minus k, and k is running from 1 up to m by 2, and for k equals to 0 we have h of m by 2. So expanding this equation, we can write like this, and you see that because the impulse response is even symmetric, right? So that means the value h of 0 should be equal to h of m. Similarly, h of 1 should be equal to h of m minus 1, and so on, right? So let's write it in a compact form. So we can write the pairs, and we say h of 0 has same value as h of m, so we can write it like this. Similarly, h of 1 has same value as h of m minus 1, so we can take this common. So when we take h of 0 common, we are left with for example, okay, we take h of 0, and because they are both same, so we take h of 0 e power j omega m by 2 common. Okay, so we have h of 0 and we have e to the power minus j omega m by 2 common. So we are left here with e power j omega m by 2, right, and plus this one, because h of m and h of 0 are same, so we just denote it by h of 0, and we just and also we take this common, so we have e power, because we have taken j omega m by 2 common, so now we are left with minus j omega m by 2. Okay, so similarly again for this term we take h of 1 common, okay, and we take e power minus j omega by 2 common, e power minus j omega m by 2 common. So we are talking about this. Okay, so when I take this one common, then I am left with e power j omega m by 2 and we already have here e power minus j omega, so we have this, and then plus and here we have because we have taken e power minus j omega m by 2, so we have e power minus j omega m by 2, and we also have minus j omega, right? So similarly we compare the terms having the same value, same h value, and different exponential value, definitely, right? So again, if we look at this one, so these two are, you see, same, so maybe we just take the j omega common here. So if I take j omega common here, then I am left with m by 2 minus 1. Okay, so again if I take j omega common, then I have m by 2 and omega. Okay, so if you look at this one, so I think you can say that this is basically going towards the cosine, because if I divide it by 2, so definitely I will also multiply here by 2, so that means this is cos omega m by 2 minus 1. Okay, similarly if I divide this expression by 2 and multiply it also by 2, so again this is cos, so it will be cos of omega m by 2, right? And these two 2's are multiplied with it, so I think for the generalized case we can replace these h of 0, h of 1 by ak, and we can write cos omega k. So this is k running from 0 up to m by 2, and because all the terms they have e power j omega m by 2 common, so we can write it here. So this results into this, right? So ak equals to 2hm by 2 minus k. So for example, for h equals to 0, for example h equals to, or let me write this just one thing, so 2h1, and this is e power minus j omega m by 2, and this will be cos, right? And this is omega, right? Cos omega m by 2 minus omega, right? So I think this is not omega, this is just 1. Okay, so we have cos of omega m by 2 minus 1. So for this one we will have something like cos of omega m by 2, and so on. So we can generalize it to this expression. I hope you can do the rest by yourself, and we can discuss if you have any confusion or any problem. So in case of type 2 FIR linear phase systems, we say that the system has a symmetric impulse response, but m is an odd integer in this case, right? So these are some examples, maybe you go through them. So the response is given by h of n equals to h of m minus n for this range, okay? And the frequency response is given by h of e j omega equals to e power minus j omega m by 2, and it is equal to k running from 1 up to m plus 1 by 2 bk cos omega k minus 1 by 2. I hope you can go do the calculations for transforming the impulse response into the frequency response, right? And in this case also beta in the equation 3 is either 0 or pi. Type 3 FIR linear phase systems are those where impulse response is odd symmetric. So in this case m is even, so h of n equals to minus h of m minus n for this range of values of m. So remember that m is even. Again, the frequency response is given by j e power minus j omega m by 2, and we have summation k running from 1 up to m by 2 ck sine omega k, where ck is 2h. So I hope you understand. You can do the calculations, or you can do how we are transforming this time domain impulse signal into the frequency domain. So the type 4 is defined as the one that has impulse response which is odd symmetric. So in this case m is odd. So h of n equals to minus h of m minus n for this range of m, and you understand m is also odd, so that means frequency response of this type of FIR linear phase system is given by j e power minus j omega m by 2, and these also, I hope these are pretty straightforward. So these are some of the examples of the FIR linear phase system that we have discussed so far. I mean those four types of the FIR linear systems. So shown here is a type 1, and we see here M is even, and the response is also even symmetric, whereas the shown in figure B is a type 2 system, and it has a symmetric impulse response. So if you look at this one, so both sides of this they have same. Okay, similarly the shown in figure C is the type 3 FIR linear phase system, and in case of type 3, which is defined as the one that has the anti-symmetric impulse response. So you can see that's the center of symmetry. So if you move this one, you see it has value -1, and this one has value of 1. So that means it has anti-symmetry, right? Or it has odd symmetry. Similarly, shown in figure D is the type 4 FIR linear phase system, and in case of type 4 we say that the impulse response is again anti-symmetric and M is odd here. Okay, so this M equals to 1, and you see the anti-symmetric property of this one. So the corresponding impulse responses and the frequency responses of the four types of FIR linear phase systems are shown here. So you see for the case of type 1, we have Hn equals to 1 for n running from 0 up to 4 and 0 otherwise, and this system has a frequency response equal to this one. Similarly, for the second case, if you look at the figure, you can see that this is M has the odd value and N is from 0 up to 5, and with the corresponding frequency response, this one. Similarly, in case of type 2, type 3, we had so in case of type 3, if you look at the figure on the previous slides, you can notice that here M equals to 2, and it has values, non-zero values at 0 and 1. At 1 it has value of minus sorry, not at 1, in fact at 2. So at 0 it has value of 1, and at 2 it has value of -1. Similarly, for the case of the type 4, that is also, you know that type 1 and type 2 they are symmetric, whereas type 2 and type 3 and type 4 are anti-symmetric. So okay, I'll just find the frequency response for the type 2, and I think for the remaining you can find. That's quite straightforward if you recall the Fourier. So you know that because the impulse response equals to h of n, and which is equal to 1 for n running from 0 up to 5, so we can take the Fourier. So taking the Fourier will result into, maybe let me write the equation. So we can write it like this, and this is summation from 0 up to m. So the summation equation is this one, right? So beta power n, sum running from k up to l. So this is equal to beta power k minus beta power l plus 1 over 1 minus beta, whereas beta is not equal to 1. Okay, so this one also, if you look at this one, let e power minus j omega is beta, so this is beta power n, so this is equal to beta power k, so k is the lower limit, which is 0 in this case, so it e power 0 minus e power minus j omega 6 divided by 1 minus e power j omega. So 0 is 1, so that we can write it like this. If we take e power minus j3 omega common, so because here it is 1, so we can write it e power j3 omega, because if you multiply j3 omega and minus j3 omega, they will cancel and result into 1. So again here taking this one. Now if you look at one, this is the equation for the sine. Okay, so again e power minus j omega, because this is in the denominator, so if you bring it to numerator, it will become plus e power j omega, then by 2, so e power 3j omega minus, right? So we have minus j3 omega by 2, and we have plus j omega by 2, right? This whole is e power, so that means they will cancel, right? Is it okay? So because when you subtract, so 3 minus omega will result into 2 omega. Sorry, this is not divided by 2, in fact this is e power j 3 omega. Okay, so 3, so if you take the LCM will be 2, so it will be 2 3s are 6 minus 6 plus j omega, so it will be e power minus j, because 6 minus 1 is 5, so it will be minus 5 by 2 omega. Okay, again if I divide this by 2j, right? So if I divide and multiply by 2j, so again I can write this division into double one, so this means that this is basically sine, right? E power yes, e power j theta minus e power minus j theta divided by 2 is basically sine theta, so it will be sine of omega 3 omega, right? 3 omega, and divided by, this will be sine of omega by 2. Okay, so this is the frequency response for type 2. I hope you can do in a similar way for type 1, type 3 and type 4. So you get the results as you get the expression as shown in the previous slide. So we end the lecture here. So to summarize this topic, we can say that we have type 1 FIR linear phase system when M is even and it is symmetric. Similarly, type 2 will be if M is odd and the response is symmetric. For the type 3, we say M is even and the impulse response is anti-symmetric, and type 4 will be the one where M is odd and the impulse response is anti-symmetric. So that's all for this lecture. See you in the live session. Allah Hafiz.